Here we are. Hello, y'all. Hang on a second. There's Noemi. How you doing? Lydia, Nicole, Ariana. Ariana Tutar, still one of my favorite names. Let's see your faces. Bring them up, please. Hey, Nicole. Where are you, Nicole? Are you
Hi, how are you?
Are you home or in Plattsburgh? Or is Plattsburgh? Are you home or in Plattsburgh?
I'm at home.
Okay.
Under a tree.
All right, we got 14 people in this class. Let's see how many people come today. Faith Haley, good to see you. Although all I see is your name. Give us your faces real quick, just so we know who we're dealing with here. Tyler Montano, connecting in from Trinidad. Am I right, Tyler? There's Faith Haley.
Yeah, you could.
So, Tyler, when I had a student from Trinidad before who said there's something called a shark bite sandwich. Is this right? Shark and bake or something?
Yeah, it's bacon shark. Yeah.
Bacon shark. Tell us about this wonderful sandwich.
Wow. I'm not really sure how to explain it, but basically, you catch a shark and you have to cut it and you fry it and you put it in like something we call baked. That's basically like bread or pie, and you put like tons of sauces on it, like and vegetables, and that's it basically.
Yeah. But you killed the shark, right? You're murderers?
Yeah, you have to go out, catch a shark, kill the shark, eat the shark. Yeah.
Oh God, you're killing sharks? How rude. Celine
It tastes
Ramos.
pretty good though.
Oh, I bet. I have to go to Trinidad someday. Celine Ramos coming in from Peru. Am I right? Celine?
Yeah, well, right now I'm in Plattsburgh because I have a in-class, an in-class, like, person class,
Yeah.
like, after this, so I have to, like, run over there.
Okay. Well, stay safe. Let me know how that works out. I'm doing all mine online.
Yeah,
So.
I'm gonna figure it out.
Okay. One, two, three, four, five, six, seven, eight, nine. 9 people. Let's wait a couple minutes. So the other person in this class with another name I love is Kaylee Quackenbush. I love Quackenbush. It's a great name. It's a woody name.
Thanks.
Thanks. Noemi. One, two, three, four, five, six, seven, eight, nine. 9 out of 14. Should we go ahead? What's 9 out of 15? That would be 3/5, 60%. All right, well, let's wait 2 more minutes. At 9:35, we'll get fired up here. I don't want to get started before everybody's here. And I have to warn you, this is my second Zoom lecture this semester, and I do a lot of jumping back and forth between different screen it there's some downtime during that, but it It should work out okay. Bezoit. Hello, Bezoit. Lemon. Connecting.
Do you record these
Yes, I'm recording it.
and you're going to post it after?
Yeah, I'll post it. I did that yesterday. It's for an hour and 15-minute lecture. It's really hard to do, and my internet is really crummy out here. I'm at my wife's family's lake house, so I will get them up. It may not be as fast as we hope, but it'll be up.
Okay, thank you.
All right, we got 10 out of 14. Why don't we go ahead? Let's, Bezoit, how you doing up there? Can you say hello? Are you hearing me? Bezoit? Gamelon. Okay. I don't think she's in this country. That's a different language. There she is. Hey, Bezoit. Bezoit. Give us a wave. Come on. Okay. All right. Why don't we go ahead and get fired up now? As long as Bezoit's here, we can go. So let's start out looking at the syllabus. Okay, so this, oh, hang on. One more thing to tell you is that I keep my chat window open. Try to anyway, keep an eye on it. So if you have any questions and you don't want to speak up, you can do that. So let's arrange my screen. Okay, so here we are. Little chatterama going here. Okay, oh, what the heck is this? So this is Bio 424, Cardiovascular Pharmacology. Here's my office. I will not be there this semester. I've got asthma, which is a pre-existing thing for the COVID, so I'm not going in, just stay safe. Here's my phone. That's my cell phone, so you can contact me here at that phone number if you need to. Email is probably the best. I check my email an awful lot. If you want office hours, let me know. We'll set up a Zoom chat for you. Okay, that's it for the. Okay, so what are we going to be talking about? So first thing we're going to talk about is classical pharmacology. So pharmacology is a discipline you probably don't know much about. You don't hear much about it in college. It's more of a graduate degree. And there are a lot of different things you can do in pharmacology, so I'll chat that up a little bit to begin with. And we'll talk about the basic drug receptor interactions that are central to classic pharmacology. And then we'll talk about receptor pharmacology, binding receptor to the drug to the receptor or the hormone to the receptor, activating second messengers. This, if you've had me before, for cell biology, is going to be a lot of review, which is good because I think a lot of times you don't remember things from one class to another. So we'll review all the 7 transmembrane receptor second messenger stuff. And then we'll talk about pre and post synaptic biology. So again, this is going to be, if you had Bio 213, we talk about synapses. So here we're going to get into synapses again, but a little more depth, a little more detail. And we'll talk about receptor regulation, which again is something I talk about a lot. So our first exam then will be September 15th. I'm not sure I'm going to do that exam yet. It'll definitely be on Moodle, but I'm just debating whether it's going to be all essays. I think it's probably going to be all essays because this is a small enough class that I can do it that way. Okay, so then the second section, autonomic pharmacology. So that's, the parasympathetic and the sympathetic system. We'll talk about the anatomy of it a little bit, and then more the function of the sympathetic systems and regulation of the cardiovascular system by the autonomic nervous system. And then we'll talk about the cell biology of the cardiac and smooth muscle cells and how these are important in controlling controlling the blood pressure and things like that. And then exam 4 That's exam 2, October 13th. And then cardiovascular physiology, which is, kind of the hemodynamics, when pressure goes up, when heart rate goes up, when blood flow goes up, stuff like that. So we'll get into that. And last, the pathophysiology and pharmacological intervention. So here's the thing about this class. I've done this, I don't know, a number of times. I do it every other year. Typically, at least a third to a half of the classes, we're sitting around reading primary literature and discussing how you read primary literature and what all this stuff means. So in terms of just lecturing and giving you stuff, I don't think I have enough to fill this whole class. So I don't know how we're going to do primary literature online, but we're going to try and do that anyway. Otherwise, I'm not really sure what all we're going to be talking about here, because that's a lot of the class, frankly. So there's that. All right. Objectives. Objectives are for you to learn. I'm supposed to fill that objectives out. I haven't gotten around to that, so don't worry about it. Grading, we will have 4 exams, and your final grade will be based on those 4 exams. I should put another thing in here for bonus points. I'll talk about bonus points later when we look at Moodle. Oh my God, A is a 93? This is ridiculous. It should be 95. I'll leave it at 93, so there's not a bait and switch on me here, but that's really old. I've increased my standards lately. Okay, attendance. So, I'm going to be recording these lectures and uploading them, so if you can't make it, that's fine. There's no need to be here if you can't be, but it's good to be here because, there's the jokes, right? There's always the jokes. Absence from class, absence from exam, you can read all that. Withdrawal policy is basically the university withdrawal policy. Do not cheat. I'll talk more about plagiarism when we get closer to the exam, because that's the only opportunity you'll have to cheat. Okay, so any questions about the running of the class? Anyone want to write a chat on that? No, we good? Okay. All right, so let's go ahead and get started with lecture 1. Oops, oh shoot. Sorry, I'm just trying to get my multimedia extravaganza put together here so I can see you, see the chat. Okay, so if you're having trouble as we're going through, just chat something, throw something on the chat, and I'll pause and answer your questions. So, cardiovascular pharmacology. When I was in graduate school, this is what I did. I got pills and I threw them at a plastic heart. That's what I got my degree in. No, I'm just kidding. Come on, you. How do I? There, okay. What is pharmacology? So pharmacology in general, classical pharmacology, is testing small molecules to find potent drugs, it should say find potent drugs to cure diseases or relieve symptoms of diseases. Okay, so it's kind of a takeoff on traditional medicine, plant herbs, using herbs to treat diseases and to cure or to alleviate symptoms and things like that. And it's kind of like an extension of that. And also, this is kind of weird. Some of the first pharmacologists were basing their work on the new industry in the late 1800s of dye making. Organic chemistry was just getting started in the late 19th century, and people were making these dyes that really stick really well to cloth. So when you dye your cloth, the first time you wash it, the color doesn't go away. It holds really fast. Aniline dyes, they were called, and that was used as the model for drugs, where you've got a small molecule, it's going to stick really hard to something, and that's where you get your effect. So Paul Ehrlich, one of the early pharmacologists, was a fan of that. Anyway, what is in pharmacology today? So if you were a classical pharmacologist, you could do work that's basically biochemistry, cell biology, physiology, cellular physiology, whole animal physiology. When I was in grad school, every now and then you'd see an anesthetized pig going down the hall underneath the drape, because there was one guy down the hall who did whole animal pharmacology with pigs. The pig heart is very similar to the human heart, so it was a good model. You could also do genetics and molecular biology. That's what I did as an undergrad. I cloned the voltage-dependent calcium channel for my thesis. And you could even do behavioral studies. So more than just physiology, but how does that change behavior? So you can do pretty much anything under the umbrella of pharmacology. What is nice about pharmacology is all these things are involved in drug development. And there are a number of advantages to having a degree in pharmacology. So if you're thinking about going into graduate school, it would be a good thing to consider. For one thing, you get a broad range of training. So if you were, in a more select thing like biochemistry, always doing NMR on proteins, then that's your skill set. But in pharmacology, you've got a broad skill set, which makes you a lot more marketable. There are many different disciplines involved in pharmacology, as I just said, and so you're pretty broadly trained, and that makes you more marketable. Easier access to grant support. So here's something they don't tell you in grad school. You can't be a scientist unless you can get grant support, at least at the university level. And grant support has gotten really, really tight in the last 30 years. When I was in grad school, I think they said something like 25% of all grants were funded. Now it's less than 5%. So it's gotten really, really tight. And the thing about pharmacology is you're a lot closer to the money. I always say closer to the money. Where is the money? The money's in healthcare. And, doctors are really close to the money. That's why they get paid more than us. Scientists are further back now. And the closer you get to that source of funding, the more grant support there is, or the more money there is. Again, when I was in grad school, my advisor had some kind of a deal. He was a little shady. Had some kind of a deal with Pfizer because he was working on calcium channel blockers, and they'd give him on a certain amount of money every year with no questions asked. Here's your money, take it. And it became this slush fund that we could do anything with, and that was really nice. We weren't buying cars, we were buying equipment, but it was nice to not have to justify every piece of equipment you needed. Pharmacology is an applied science, so it's applied versus basic science. Basic science is when you're trying to figure out a specific mechanism in something. So you could be working on things that are very esoteric and don't seem to have a practical application, which is fine. Basic science is important, but pharmacology is a lot closer to being applied to actually helping people. And that's a nice thing too, clinical relevance and helping people. So really good job prospects. If you read the, let me share something else real quick. Where am I? So I've got a link here from sciencemag.org, and it talks about, it's from 1999, so it's a little bit old, but still relevant today. And basically it's saying that, in drug companies, again, close to the money, that's where the money is, you'll get paid a lot more there than if you're a university professor. In drug companies, there's a lot of basic research going on, but if you're going to get that drug to market, you need a pharmacologist. You need a pharmacologist there to ensure that the drug is safe and effective, and come up with all the information that the FDA wants to see. So let me go back to sharing my PowerPoint. I think I did this already. Yeah. Pop. Oh. Oh, I didn't give you that last one. Excellent job, prospect. So that's what I was getting to there. As a pharmacologist, you can make good money. I know I'd be making twice as much now if I was in industry, maybe more, maybe 3 times. So there's really good money in industry if you're a pharmacologist. Everybody likes money. Okay, classical pharmacology. What is classical pharmacology? Well, classically, what people would do is start with the traditional medicine, right? Like, for instance, foxglove. Foxglove is a plant, a flower, very pretty flower. You can look it up online. And it's very toxic if you take a lot of it at once, but a small dose of it can make your heart stronger. And someone with congestive heart failure, they would call it dropsy back in the day. Give them some of this and their heart would get stronger and they'd be better for a while. Basically relieving symptoms, but not solving the problem. You take that plant-based medicine, you do some phytochemistry with it, and you isolate you isolate all the individual chemicals, you find out which one is most active, and now that's going to be your medicine. You take that medicine to figure out how it works, it works at the whole animal level. What is it actually doing? So you can, isolate individual heart cells, you can isolate whole hearts, whatever it is that you want to work on, and figure out how it is working. Then go back to the whole animal to determine safety and efficacy, right? What is the dose range that it's effective at? What is the dose range that it's toxic at? What is your safety margin there between those two things? And how good is it? Does it, improve cardiac function 1%? Well, then who cares? But if it improves cardiac function a lot, hey, we got something here. We could help people with it. And then once you get through the animal studies, then you do clinical trials. I think we're going to talk about drug development sometime in this class. But basically, you've got 3 stages of clinical trials. The first is healthy volunteers, just to make sure it's safe. And then it's like you've got this next step is affected people. So you've got a control group and the affected group, and you see if it works, and then usually you compare it to other drugs that are on the market at the same time to see if it's better than those. And if that's okay, then you go to a larger group of people, volunteers who are affected. When they talk about, someone's got cancer and they got included into in a clinical study for this new drug, that's what we're talking about, phase 3 trials of drugs. And then once that gets, if you're successful there and the FDA approves the drug, boom, it's on the market. One of the problems, drugs are so friggin' expensive today, and I think a lot of it's just greed, but to a certain extent though, that whole process of finding the chemical and getting it to market takes about, 10, 12 years, okay? And then once, say about 5 years into that process, you patent your drug. Once you patent it, you've got 15 years. So basically, once your drug gets on the market, you've got 7 years to recoup all that investment you made into the drug before it can become generic and the price can drop. So that's part of the reason why drugs are so expensive, but also, it's a business, so people are getting a little greedy at that end. Okay. That's FDA approval, thank God. Okay, classical pharmacology. New, more modern classical pharmacology is, instead of starting with a plant, a promising plant that you can isolate compounds from, you start with a library of compounds. So you've got your organic chemist working away, making random chemicals, all kinds of chemicals. You put them all together and you test them, and then you try and find out. That's high throughput screening. It's kind of like the COVID tests they're doing today. Interesting little diversion here. So one thing they're doing a certain amount of, although I think they should do more of, is grouping tests together. So for instance, you've got 100 tests to run. Well, instead of running 100 individual tests, run 10 tests, and each test has got 10 individuals in it, right? If those 10 individuals are all negative, boom, you've done one test and you've eliminated 10 possibilities, right? If you've got another group of 10 people that comes up positive, then you do 10 tests on those 10 individual people. You've saved a lot of time, you've saved a lot of money. So that's kind of what high throughput screening is. You get a whole ton of chemicals, you test them in your system in batches, And whichever batch comes out positive, you then isolate, you separate those individual chemicals, and you work on individual chemicals after that. So bottom line here, in more modern drug discovery, you've got a shit ton of that, which is a technical term, shit ton of chemicals, and you screen them all to find out what's going to be most active. Then you isolate 2 or 3 lead compounds, and you do your in vitro studies with that. And then you do your whole animal studies again, clinical trials, and FDA approval. So that's more modern drug discovery. That's what you see a lot of today in drug companies. Reverse pharmacology is another interesting new mechanism, in that you start with your target. You know, molecular biology has made this possible. You know, why does someone have muscular dystrophy? Well, then you don't have a drug and you're trying to cure muscular dystrophy. You're looking at the mechanism. Why does this muscle not work? Oh, this protein is wrong. What do we do about that? Now we find some drugs to interact with that protein. So you start with your protein target, and then you use your chemicals to identify the active species on that target, perform your in vitro studies, and FDA approval. So basically, earlier I was talking about what pharmacology is important today in drug companies. This part, this start with the protein target, that's all basic biology and chemistry. That's what most graduate students are going into, looking at that. And this stuff from perform through FDA approval, that's all pharmacology. So drug companies really need pharmacologists to get drugs on the market, and that's why. Okay. I'm going to stop bragging about pharmacology from now on. If anybody wants to know more about pharmacology and how you get into it, let me know and I can help you with that. Okay, but we're going to start out, let me turn my phone off here. We're going to start out talking about the drug receptor interaction. And I've written up several pages on this, and I've posted them on Moodle there, and you should read through that. What I'm realizing is it took me about 3 weeks to come up with this one lecture written out like that. So what I'm going to have to do in the future is just do an outline version of it in PowerPoint. So I'm going to do outline in PowerPoint, which means if you want to read in more depth, you're going to have to get some internet resources. I will do my best to post some when I get them, but I've got 4 classes this semester. It's coming at me like, I don't know how much I can get up there. If you look at your Moodle page, I say something about bonus points. So if you can get me some video or some other really good resource on the things we're talking about, send that to me in an email. I'll post it up into Moodle for everyone to see, and then I'll give you bonus points for doing that. So we're kind of all working together on this. And believe me, there's nothing new here. This is all out there. There's tons of sources on this. Some are better than others. So if you find anything good, send it to me in a link and I'll give you bonus points for it. Okay, so, but what are we talking about? So in the end, we'll be talking about drugs producing effects. How does that happen? Well, it happens because you've got your drug or ligand. Ligand's a general term that means something that sticks or something that binds. So it's a general term. So it can refer to your drug, could refer to the endogenous hormone, whatever. So we've got a ligand. It's going to bind to this membrane receptor. And I'm pointing. Look at me. I'm pointing at my screen. It's going to bind to the membrane receptor. It's going to change the conformation of that membrane receptor. Oh, shit. Oh, shit, oh, shit, oh, shit. Sorry, I accidentally clicked on that thing. Oh, stop. I'm sorry. Hang on a second. So here's something I can tell you while you're waiting for me to get my shit together. Anytime you see anytime you see a figure like this that's not mine, something I got from the internet, if you click on it, there's a link there that'll take you to where it originally came from. And that's kind of the citation, okay? So if you take a picture from the web, that's plagiarism really. It's a type of plagiarism unless you cite it somehow. So that's how That's how I cite things, is by putting the link in with it. So that's there. And what just happened was I've got this touchpad on my laptop, and it like perceived that I had clicked on it, and we went to that site. Okay, enough of that. So anyway, this is what we're talking about. Drug binds to receptor conformation changes, and that causes an intracellular response. So today's lecture is basically just that first step, the ligand binding to receptor, and then the ligand coming off the receptor. This interaction, unless I say otherwise, is non-covalent. There's at least one drug we talk about that is covalent, but for the most part, all our drugs are non-covalently binding to the binding site. And it's very specific, just like putting a key in a lock. It's very specific, that drug or hormone, that ligand going into the binding site. So here you can see an example of this. This is a model of epinephrine binding to the beta-adrenergic receptor. So here, with this green outline is epinephrine. Can you see? Okay, I can only see Nicole and Bezuit and Kaylee's faces. When I'm doing my cursor here, can you see my cursor? Up and down is yes. Yes, okay. So this is epinephrine here. Thank you. This is epinephrine. And what we've got here is a 7-transmembrane receptor. The beta receptor is a 7-transmembrane receptor. So you've got 1, 2, 3, 4, 5, 6, 7 transmembrane segments. So these segments come together. Well, usually when you see them, they're like spread out like this in a diagram, but they come together like this. And in the middle of that, deep down in the middle of that, is the binding site. So first, the ligand has to find its way down in there, which means as these molecules are hitting this receptor, just randomly hitting it from different directions, most of the time that is going to bounce off. But every now and then, one will hit just right and slip down into it. Now, once that ligand gets in there, it has to be in the right orientation to perfectly align with the amino acid side chains that are there. So here you can see epinephrine has got this big phenyl ring, and on transmembrane region 6, there's phenylalanine, amino acid number 290, and you get pi-pi interactions between those two rings. So that's a non-covalent interaction. Over here, you've got 2 alcohols off this phenyl ring, and over here on segment 5, you've got 2 amino acids, serine, and now you're getting hydrogen bonding here between this alcohol and this alcohol. Okay, I mean this alcohol and this alcohol, this alcohol and this alcohol. So you've got these polar interactions here, hydrogen bonds. Hydrogen bonds are pretty strong polar interactions. At the other end of the molecule, epinephrine has got a nitrogen here and a methyl group after it. This nitrogen then, because you end up with 5 or 4 bonds on it, there's a hydrogen behind here, has a positive charge. And here on transmembrane region 3, you've got an aspartate that's sticking out. And that aspartate then interacts with the nitrogen. So here you've got an ionic bond. So this is kind of interesting in that you've got 3 different types of non-polar interactions between the ligand and the receptor. You've got your ionic interaction, which is the strongest non-covalent bond. You've got pi-pi interactions, which are weak, but at least it's hiding those pi electrons from the water solution. And then you've got hydrogen bonding there. So you've got a really tight interaction there, very specific between the ligand and the receptor. And that's what we're going to be looking at here. Like, well, not specifically functional group stuff, but like how do you describe that interaction in quantitative terms? How do we describe how tight that binding interaction is? Here's another drug over here, phenylalanine, another ligand. You can see comparing this to epinephrine, you've got this big phenyl ring still, right? And you've also got 1, 2, 3 things out. You've got a nitrogen, so you can interact there, but there are no hydroxides on this end, right? No alcohols. And so it's not going to have this interaction. So this phenylalanine will not bind to this receptor. won't bind to the beta adrenergic receptor at all. It binds to the alpha adrenergic receptor really well, but not at all to this one. So every little structural change you make to that ligand is going to change the binding of the ligand to the receptor. Actually, it will bind to the beta receptor, but not well. You have to go to a really high concentration to get it to bind. So that's key too. When we say a strong interaction, it means it binds at a really low concentration. A weak interaction means you have to go to a really high concentration to get it to bind. And so we'll talk about that and how that affects potency. So anyway, this is what we're talking about. The receptor, the drug interaction with the receptor. Okay, bad news. We're gonna do some math now. Everybody likes math. So this is your classic rate reaction stuff from Chem 112, which you took freshman year and hoped you would never see again. So I'm not going to expect you to be able to do this derivation or to do this on a test or anything. But I want you to know, when in science we've got an equation that becomes our model to explain something in the natural world, where did that come from? It comes from like basic first principles, and then you derive what you need from those basic first principles. So here in this reaction, what we're going to be deriving is the binding isotherm. In other words, how this drug binds to this at one temperature, isotherm, one temperature. So how do we derive this equation that's going to describe the binding? We started out talking about how this is our simple reaction. You've got the ligand is going to find the receptor and bind to it. And you've got a certain rate that that's going to happen at. And then once that ligand is bound to the receptor, eventually that ligand is going to come off the receptor. It's non-covalent, right? So it finds the receptor and it makes those bonds. And whenever you bond, you're decreasing the energy of the system, and that's what holds it there. But water molecules are constantly bombing that thing, and eventually it'll pick up enough energy to fly off. So that's our reverse reaction. The ligand binds to the receptor in the forward reaction, and then the ligand comes off the receptor in the reverse reaction. And we've got a different rate constant for each of those interactions. So the rate of formation of LR then is equal to its rate constant times the concentration of both of these, right? Because we've got two molecules going into this interaction. So if you increase the ligand, it's going to happen faster. If you increase receptor, it's going to happen faster. So it's based on the concentration of both. Rate of dissociation then, you've got only one molecule there, or one thing there, which is the ligand receptor complex. And at a certain rate, that ligand will come off the receptor. The rate of formation, rate of dissociation. Now at equilibrium, which means, you say you're doing some test tube, you've got receptors in there, you add your drug. At first, it's going to be all rate of association because there's no LR at all. And then over time, as you get more LR forming, you're going to have the other reaction happening where you've got that ligand coming off. You wait enough time, and usually a couple hours, to make sure. You wait enough time, the rate of formation equals the rate of dissociation, and that's equilibrium. So when you get to equilibrium, then your rate of formation equals your rate of dissociation. So our binding isotherm is at equilibrium. Okay, so we rearrange that because we want to get rid of our constants. So we rearrange that last equation and we get K2 over K1 equals LR, L times R over LR. And now we're going to redefine this. Why have two constants when you can have one? So we get rid of this. Hang on one second. Where the hell am I now? Okay, so now we redefine K2 over K1 as KD. KD is going to be really important to us. So KD is our dissociation constant. It includes both the association and the dissociation, but we call it the dissociation constant, KD. KD then describes our attraction between the ligand and the receptor. So it's all based on these interactions between the functional groups on the ligand and the functional groups on the protein. So how well does that ligand fit into that pocket is going to determine our KD. And it determines what concentration is needed to occupy the receptor. Let me see what I say next. So KD is the concentration of the ligand that will occupy half the receptors. So when you've got a ligand concentration that's equal to the KD concentration, half the receptors have ligand on it. And that helps us determine the potency of the drug. So in kind of lay terms, when you talk about a drug being potent, usually we think that means it's strong. It's a really strong drug. But that's not what it means in pharmacological terms. In pharmacological terms, potent means potency is what concentration you need to get the effect, and not at all related to how strong the drug is. So the KD determines what concentration the drug will bind to the receptor. So then when you go to the next step of getting an effect from that drug, the concentration you need to bind the receptor is going to affect how much you need to get the ultimate result there. So KD then helps us to understand the potency of the drug, and we'll talk more about KD later. So, okay, KD is specific for each ligand's reaction with each receptor under specific conditions. So each different ligand you have with one receptor will have a different KD. Each ligand will have a different KD at different receptors. So it's all based on that specific interaction between the functional groups. And when I say under specific conditions, I mean that if you isolate those receptors from the tissue, put them in a buffer solution, that buffer solution is going to help to control the shape of the receptor and therefore the binding of the ligand to the receptor. So the conditions have to be constant if you want to compare across different drugs or different receptors. So things like ionic strength of the buffer, pH of the buffer, temperature, everything that affects every molecular reaction is going to affect the KD. I have it right there. Structure of the receptor and the ligand, ionic conditions, pH, temperature, state of the receptor. So we'll talk about that later too, about how the cell can change the receptor and that will change how well ligands bind to it. So we'll talk about that eventually. Okay, maximum binding. So Bmax is another thing we're gonna need. So let's back up for a second here. Come on. So right now, this is where our binding isotherm is, and all we're looking at is KD, the affinity, versus the concentration of these things. So later in this lecture, we'll talk about how you actually do these experiments, and you do that by labeling the ligand with radioactivity. Whenever something's radioactive, it's easy to find, right? It's giving off radioactivity, it's easy to find. So if you look at this equation, we can always measure this. We can always measure this because it's got ligand on it. This is something we can't really measure because it's a protein and there's no specific way to measure that. So we're going to get to that. And this is what we want to know in this next step is how many receptors are there. So that's what our Bmax is about. So Bmax, excuse me, Bmax then is the amount of ligand that can bind to the tissue. So Bmax tells us what's the maximum amount of ligand that will bind to the tissue, which is the maximum number of receptors in that tissue. How many receptors are there in the tissue? At Bmax, every one of them has a ligand on it. So Bmax then is a measure of how many receptors are in that tissue. Receptor density, we call that because it comes out as a concentration. The units end up as concentration. So some tissues have a high density of receptors and some have very few. So if you look at your arteries have got a very high density of alpha adrenergic receptors because it's really important to their regulation. If you look at the liver, very low concentration of alpha receptors because it's not that important in liver. So every tissue is going to have a different density. And one of the things we can find out by doing this is how many receptors are there. So that's another important factor that we'll get out of this. Okay, how do we find Bmax? Good question, I'm glad you asked. So total number of receptors then is the number of free receptors plus the number of receptors that have ligand bound to it, right? You put a certain amount of receptors in your test tube and then you add your drug. Some will have ligand bound, some won't. So Bmax then, your total receptor concentration, is adding them both together. So, I just said this. In binding experiments, we can only measure the ligand. Free receptor will be unknown. LR is measured. So we can know free ligand, we can know free ligand receptor, but we can't really know receptor. So we're going to take this Bmax equation here, rearrange it to solve for the thing that we can't know, R. Okay, so R is equal to Bmax plus LR. Now we can substitute Bmax plus LR into this equation so we can get rid of this thing we can't know. Once we do that, we know this, and we're determining this and this. So here's our binding isotherm here. This allows us to find out both KD and Bmax by doing our experiment. Now, this is not the best way to look at this, because when we do plot this out, we're going to be plotting on the y-axis the concentration of free ligand, which is this, and on the that's the x-axis. And on the y-axis, we're going to be plotting this. So we need to isolate the LR. So again, a lot of algebra, not that hard, but I'm not going to expect you to know it. But you do this algebra and you end up with this. So this is the equation you should know. This is LR is equal to Bmax over 1 plus KD over L. So now we can take this and we can plot L versus LR, and we can find Bmax and we can find KD from it. This is our binding isotherm. So when you're doing receptor binding, this is the equation that's going to describe the curve that you get. So, and you can tell this is not a linear equation, right? Linear equations are y equals mx plus b. This is much more complicated than that. This is going to give us what is this? What do you call this? Quadratic? I don't know. This is a non-linear equation. Listen to me, Mr. Math over here. This is not linear because it's not a straight line. Okay, so this is our binding isotherm. This is what we get out of it. So what do we learn from this? So the data then is ligand. This is our independent variable. This is in our experiment, we determine what ligand we're going to add. This is our independent variable. So this is the result we get from our experiment. And we plot this versus that. And we find when you go to high enough concentration of ligand, we will saturate the receptors. When every receptor has got a ligand on it, that's Bmax, okay? So that tells us how many receptors are there. And then something I defined earlier, our KD, which is a really important value, is 1/2 of the Bmax, okay? And I just thought of a really cool animation to make. Maybe I'll have time to make that before next time. But if you increase the if you decrease the affinity, KD is going to shift out this way and your curve's going to look more like this. Okay, take a lot longer to reach saturation. If you make the affinity greater, KD is less and your curve gets a lot steeper. Okay, so that's how you can tell the difference. You have two different drugs, how you can tell the difference in their KD, or the difference in their affinity by where their KD is. Now, a graph like this is really hard to look at if you're trying to compare KDs, because there's very little difference between concentrations down here, because we're on a linear scale, and these things happen on a log scale, not a linear scale. So we make a semi-log plot, and that's what this is. So the log of the ligand you added versus the ligand binding, you get this nice sigmoidal plot. So then the KD is equal to, again, 1/2 the Bmax, and you can estimate Bmax based on where you're saturating those receptors. Typically with this nonlinear curve like this, in the old days, you would just plot it out on graph paper by hand, and you would estimate where your KD was. Today, what you would do is put your data into a nonlinear least squares algorithm, and it would give you KD and Bmax. So like when you're in lab and you're doing a linear thing like absorption versus concentration, right? You would click on your data and say, give me a trend line, right? And it'll give you a linear trend line fit to y equals mx plus b. Well, this is a nonlinear trend line fit to your binding isotherm. You would put your equation in and say, fit my data to this. So anyway, that's how you find KD and Bmax, is by doing your experiment and then plotting it out. Another thing we learned from this plot, which is really important, is you should have 2 log units between 10% of Bmax and 90% of Bmax. So why is that important? So that tells you the slope of this middle part of the curve. And if you've got 2 log units between 10 and 90, that means you've got a simple bimolecular reaction. They're just interacting with each other and coming off, just like we've been talking about from the beginning. If your curve is steeper than that, so you've got, say, one log unit between 10 and 90%, that means that one molecule binding makes it easier for another molecule to bind. That's cooperative binding. So if one molecule binds and makes it harder for another to bind, then your slope would be more than 2 log units for 10 to 90%. That whole business is not that important. It's not life and death for you guys right now. But just so you know, another important thing we get out of this is you've got 2 log units between 10 and 90%. And so that is your, that tells you it's a simple bimolecular reaction. Keep that in mind too later when we're talking about classical pharmacology, because classical pharmacology is looking at a lot more complex, not classical pharmacology, dose response curves, because that's about a more complicated interaction than just bimolecular interaction. Your drug binds, activates intracellular processes, those processes activate other processes, then you get the effect, much more complicated, but you should still see the same curve. And if you don't have that slope like that, then you've got something complicated going on that's more than just a simple interaction. And also, when you think about this, when you're taking a drug, right, you take twice as much of a drug. Do you get twice as much of an effect? No, you don't. If you took this much drug and you doubled it, you would get this much effect, right? If you increase by 10-fold, then you get that much more effect. So the dose response curve is not linear, it's a log scale. That's why, if a doctor doubles the dose of your drug, probably do more, but not like crazy more anyway. All right, so kind of to review here, what do we learn from these graphs? We get an estimate of Bmax, right? Receptor density of the tissue tells you how many receptors are in that tissue. We learn the KD, which is the affinity of the drug or of the ligand for the receptor under these conditions, caveat. And we also learn whether the interaction is a simple bimolecular reaction. If you've got that nice slope in the middle, then it's a normal reaction. Okay, questions, comments? Let me pause for a second here. Check out the chat. Come on, chat. Chat. Why is my chat window not opening? There it is. Okay. This is where you chat. So I'm looking for feedback here. Does this all make sense? Is this complicated? This is yes. Oh, of course I asked 2 questions. Is this complicated? Yes, no. 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 We're good? We go on, we learn more. Can we learn more? Can we learn more? Oh, I don't know why you guys put up with me. Okay. So let's go back and learn more. I gotta tell you, I don't know why they pay me sometimes. This is so much fun teaching you people. Not saying they shouldn't pay me. I have children and they get hungry. Okay. So it's funny, speaking of children, I'm sitting here on the porch of this camp, and there's like, I can show you, there's like a screen to look outside there. And I'm sitting here talking to you, and I see my 10-year-old daughter run by outside with a stick like this. I'm like, I don't want to know what's going on out there. She's crazy. Okay. Okay, so we talked about the theory of everything that's going on. Now let's talk about how you actually do this experiment to get this data. So first step is to make your ligand radioactive. A lot of all your common ligands that you want to use for a known receptor are going to already be available commercially in a radioactive form. And by radioactive, I mean they will substitute a tritium for a normal hydrogen. And that tritium is going to decay. I think it's got a half-life of something like 1,850 years or something. So it's not like extremely radioactive, but it's radioactive. Like if you do, I don't know if they still do this in molecular biology, but we used to use P32, radioactive phosphorus, and that had a half-life of 14 days. So that was really radioactive. It was like screaming hot. This is radioactive enough that you can detect it. So that's tritium. And basically you've got hydrogens in your structure, replace one with a tritium, bingo, you've got a radioactive ligand. And those beta particles then are detected by scintillation. So you can't really measure the beta particles. What you measure is your ligand will give off a beta particle. Beta particle is basically like a positron, I think. It's like an electron. It's got the same mass as an electron, the same charge, but the opposite charge. So your beta particle then will come out. It will hit one of these scintillators, which is a molecule that will absorb the beta particle and give off a photon. So every time you get a decay in your ligand, you'll get a flash of light. And then you've got your detector over there. And the detector is similar to a spectrophotometer, except typically it's round. So you put your little tube of stuff you want to detect into it, and it can detect on 360 degrees whether a flash of light is coming out. And then it measures every individual flash of light, and then the number of flashes then is directly proportional to how many ligands are in there, which is directly proportional to how many receptors are in there. So you bind your ligand to your receptor, you put it in the scintillation counter, and then you detect how many ligands are there, and that tells you how many LR interactions there are. Okay, so there are a number of different ways that you can do this experiment. They all start out the same way, similar ways, maybe not. Let's just go through them and I'll explain. So this one I'm going to talk about in detail, so I'm not going to talk about it now. So here's one way you can do it. You have your test tube with your buffer in it, and then you see this blue is the solution of your buffer. You put your receptor in there. Now the receptor is usually in a membrane. So you've got these big kind of liposomes with receptors in them, and they're heavy. They're big, chunky, heavy things. You add your radioligand there, it binds to the receptor, and then that's heavier than free ligand, right? Ligand bound to that liposome is heavier than ligand floating around. So you centrifuge it, all the, really high rate of speed, you bring down all the receptors, you take off all the free ligand from the buffer, you wash it a couple times to get rid of all that free ligand, and then you put that centrifuged pellet into your scintillation fluid and you count it. Okay, that's one way to do it. This is your scintillation fluid, this yellow stuff here. Okay, another way to do it, a newer way, is you've got those 96 well plates, right? Everyone's using 96 well plates because you can do a whole lot of experiments in a small area. So you take your plates, you fuse your receptors to the plate, you put a solution in there, and then you add your radioligand. You let it equilibrate, you suck out that solution, you wash off all the extra, and then you put scintillation count fluid in those wells, and you count radioactivity. That's an easier way to do it. This is the way I did it way back in the day, like way back before you guys were born. I did these experiments 1986. Hello, who's old now? The way you do these experiments is you get yourself a whole series of test tubes, right? Usually we would do everything in duplicate. So you'd have a series of test tubes, and each duplicate would be a different concentration of ligand. And then you put receptor into each one of those test tubes, and then mix it up, put ligand into each one of those test tubes at higher and higher concentrations, mix it up, put it at your temperature, your equilibrium temperature. You let it sit there for a couple hours till it reaches equilibrium. And then you've got this big apparatus that you would like put these little hoses down into those test tubes and that was a mistake. Suck all that out and put it through a filter paper. So the free ligand will go through that filter paper and get washed off, and then the ligand receptor gets stuck in the filter paper. And then you rinse that filter paper off several times with ice cold buffer, ice cold so you're not causing the ligand to come off the receptor, you're freezing it there. So ice cold buffer through it to clean it off. You take that filter paper and you put it in the simulation counter. So here's our wash, right? You've got ligand bound to receptor. When you wash through, all the unbound ligand comes off, and it's important that it's cold so you're not washing off bound ligand. Okay, so that's in general how it's done. That's how you bind ligand. Now, one of the technical problems with this experiment is that ligands will stick to anything at high enough concentration. So if you say you've got 10% of your ligand bound to the receptor, that 90% that's left over, the free ligand, could stick in the membranes, it could stick to the walls of the vessel, it could stick to the filter paper, it can stick to just about anything. So we want to find out what is specific and what is non-specific. All that other stuff is non-specific. Specific binding is the drug binding to the receptor, and that's all we want to know about. So how do we determine what's specific and what's non-specific? Well, what we do is compare total binding to non-specific binding. So in our total binding, we add our, just like I said, you add your radioactive ligand to your receptor, you bind it, see how much is left on the filter paper. In non-specific then, you add a high concentration of cold ligand. So the cold ligand is going to outcompete all the radioactive ligand because you got more of it there. So you're basically covering up all the specific sites. So the only binding that's left is the non-specific binding. So then you plot out down here your total binding here versus the non-specific binding. And what you're going to see is that the total binding will saturate. And then when you get to a high enough concentration, the total binding is increasing at the same rate as the non-specific, which means your receptors are saturated, and any more binding you're getting is just to these non-specific sites. So then you can basically mathematically subtract your non-specific line from your total line, and that gives you your specific binding. Okay, so those plots I showed you before were just specific binding without the non-specific binding. But if you did this experiment without the non-specific, this is what it would look like, okay? And you need to subtract your non-specific from the specific to get, or from the total to get that specific. That make sense? This is yes? This is no? Yes, makes sense? Good, okay. All right, so a lot of you had me for cell biology already, right? So I talked about this in cell biology. Now this isn't important for this class, but I want to show you it's the same thing. So this is when we were talking about transport across a membrane. And the example here was transport of glucose into the red blood cell. And at that time I said you've got, when you do your experiment, you've got total transport, but then you've got simple diffusion just going through the membrane and into the cell. That's linear diffusion. So you've got transport through these protein transporters, and then you've got simple diffusion. So to see what's going on with the transporters, you have to subtract the simple diffusion from the total. We're doing the same thing here with ligand binding. We're subtracting that non-specific from the total. Anyway, and there's your curve. Increasing concentration of ligand gives you higher binding of receptor to ligand, blah, 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 blah. Okay. Okay, why are we doing this? What did we learn? One thing we learned is the KD. So if you've got a new drug, you're going to want to know what its KD is. How well does it bind to that receptor? Hang on a sec, I'm losing my cuter here. Okay, so if you got a new drug, you're going to want to do binding experiments to find out, give you an idea what its potency is going to be about. On the other hand, you may want to learn about the receptor. So say you've got a known ligand like epinephrine, and you're binding it to a certain tissue, you've got a certain KD there. You bind it to a different tissue, you got a different KD. Well, that tells you there's a different receptor there, because the same drug and the same receptor is going to give you the same KD. So a lot of what we know about adrenergic receptors is because of experiments like this, where you've got one ligand and you test it against different tissues and you find out what receptors are there. So one of the early things that was learned was there isn't one adrenergic receptor. There's at least two adrenergic receptors. So they were called alpha and beta. And then when they did even more studies, they found out, oh, there isn't one beta receptor. There's at least three beta receptors. There's beta 1, beta 2, beta 3. Alpha receptors, there's at least two, alpha 1, alpha 2. So they found this out by determining the KD of one ligand against different tissues to find different receptors in different tissues. So that's another thing we learn through these binding experiments. We learn about the receptor as well as about the drug. And again, I keep stressing this because it's kind of counterintuitive. A smaller KD means higher affinity. A larger KD means lower affinity. So keep that in mind. Another thing we learn is about the Bmax, okay? And what we're going to determine is, A, are there any receptors for this ligand in that tissue? B, how many receptors are there for this ligand in that tissue? And C, how do those receptors change in different disease states? So what you'll see often is, like, I think the example I give in that write-up I gave you was congestive heart failure. So heart failure is when your heart's not pumping hard enough to meet the needs of your body. So that's heart failure. So what you find is the heart that's failing has fewer beta adrenergic receptors than a normal heart. So that's an important finding that we get through these binding experiments. And we can talk later about why that is, but another important thing we learned here is different Bmaxes in different conditions. And there's a paper I think we're going to read and talk about where they show differences in certain receptors. I think it's calcium channels, which are the receptors for a drug in sepsis. Okay, so in bacterial infection, the number of receptors changes over time. So that's something else we learned through binding experiments. Oh, and that's it, we're done. Just like that, we're done. Okay, so I want to open it up to the floor for questions. Anybody have any questions about this? Nobody, okay. Can I see all your faces once real quick? Ariana, miss your face. Olivia, miss your face. Celine, you know. Tyler, Faith. Can I see you real quick? There she is. There's Olivia, Ariana, Faith. Faith we've seen already. There she is. There's Celine, Noemi, Tyler. Tyler, my friend. Tyler refuses to show his face. He's probably out in the bathroom or something. All right, let's not worry about him.
Oh, my webcam doesn't work.
Oh, okay. Well, that costs you 5 points. I have to detect 5 points per lecture for that, but don't worry about it. You'll probably still pass. Kidding. Okay. All right, that's about all I have for today, guys. I wouldn't be surprised if my lectures were shorter than an hour and 15 minutes, because normally I spend a lot of time writing on the board. Now I'm just kind of BSing here. So they may be shorter than this in the future, but, and like I say, I'm not going to be writing whole paragraphs out anymore. I'm just going to be doing outlines because I just don't have time to do that all at once. But that's what we're going to do going forward. Okay, everybody happy? Yes? Everybody happy? Kaylee's happy. Noemi's happy. Noemi, I'm getting seasick. You're moving too much. I'm getting seasick. Oh. All right, I'm going to end this chat. Ending in 5, 4, 3, 2. Bye, guys.